just like yesterday.
All right, good afternoon, everyone. So you're either seeing this Thursday afternoon or Monday. I'm assuming you're probably going to see it Monday because this will be our Monday topic. Okay, you should be working on your Galaxy test as well and hopefully finishing that. Okay, that's the plan. Okay, so let me hide this here. So the next thing we want to talk about, let me go back a minute. Talked about spectroscopy yesterday, right? And the spectroscope allows us to identify based on absorption spectra, right? What elements are in a star. Okay, so the absorption spectra can tell us what elements we find in the atmosphere of the star. Okay. Next, we're going to talk about what the color of a star reveals to us. And if you look out in the night sky, and you look at stars long enough, right? Initially, they all look white, right? But if you look long enough, you'll notice that some are blue, right? Some are whiter. Some, like our sun, is kind of yellow. Some stars are red. There's different colors, and those colors correspond to temperature. Right? It says that right here. The color of starlight reveals the surface temperature of a star, not the interior temperature. The interior temperature at the core, 15 million degrees Kelvin. Okay? But the color that we see of the star indicates the temperature at its surface. Blue being the hottest, then white, then yellow, then orange, then red, and so on. And all this is governed by what we call blackbody radiation. Excuse me. Blackbody radiation is kind of a theoretical term talking about an object that can absorb and emit radiation perfectly. But we say it's blackbody because it doesn't reflect. So there's no reflection, but it can absorb and emit perfectly. So without reflection, you can't see it. So we call it a blackbody. Okay? And again, it's just theoretical. So the title of today's topic, Star Color, Temperature, and Blackbody Radiation. So a blackbody is a theoretical object that is the perfect absorber and emitter of radiation. So it doesn't necessarily mean that that object is black, but the fact that it reflects zero light. That's what blackbody is referring to. And I'm not, concerned with the definition. So blackbody radiation is produced by any object that we would consider hot. Okay, hot is anything above absolute zero. Right? Absolute zero, negative 273 degrees Celsius or 0 degrees Kelvin. So anything that is above absolute zero is considered hot, right? So everything in the universe is giving off radiation since all things are above absolute zero. Once the universe reaches absolute zero, all atomic motion ceases, everything is frozen, everything is stopped. Our universe is not at that point. So when a black body gives off light, whether that light is X-rays or radio waves or visible light, we call that black body radiation. Temperature affects the radiation that is given off. The hotter the temperature, the higher the frequency of the wavelength, meaning the bluer the light is. So the temperature of the object affects the blackbody radiation emitted, and follow along with the mouse. As temperature of the object increases, the blackbody curve shifts towards higher frequencies. Okay, higher frequencies or shorter wavelengths are more energetic, right? That's the blues. The reds have longer wavelengths or lower frequencies. Okay, I'm just going to pause it. My throat's kind of itchy. I need a drink of water here. I'm just going to hit pause. I'll be right back. All right, sorry about that. Got my bottle of water, so in case it starts again, I can just keep going. So this image here shows us the black body curves. Okay, so here we have this rainbow. This represents the visible light, right? The wavelengths of visible light. Lower, lower wavelengths or higher frequency or more energetic is on this side. Lower energy is on this side. So here we would have like gamma rays, and then X rays and ultraviolet, and then we get into visible light, and then here we'd have infrared, right? Then microwaves, radio waves, and so on. So the y-axis here is radiance, right? How much energy is coming off, how intense the light is. And then we have wavelengths on the x, and that is what color is the light, right? What is its wavelength, or conversely, what is its frequency? So if we look at this curve here, the first one, that's 7,000 degrees Kelvin, okay? So that's just slightly under 7,000 degrees Celsius. Just assume it's Celsius. Okay, you should already know the distinction between Kelvin and Celsius, right? Each degree is the same size, but 0 degrees Kelvin, which is absolute zero, is negative 273 degrees Celsius. Okay, so the hotter the object, the greater the intensity. So if we look at this curve here, this top one, right? This top curve is for 7,000 degrees Kelvin, right? So the surface is quite hot. And if we look at the curve where its peak is the greatest, we see that an object at this temperature will be around, will be in the blue purple zone. So this object, the most intense light, it'll have a bluish tinge. All these colors together give us white. And just give me a second here. Sorry about that, just helping a student with the Galaxy test. So, remember visible light. The light you see, white light, is made up of the rainbow of colors. Right? So all these together at equal intensity would create white. A hot object at 7,000 degrees here, right? It's gonna, all of the colors are represented, right? So you're gonna get white light, but it's strongest in the purple blue range. So if this was a star, it would be a blue white star, right? It would be white, but with a bluish tint, right? This star here at 6,000 degrees, okay? If we look, the peak intensity is right in this blue here, right? So we see a lot of strength in the blue, right? And we still see, if you look at the curve, a large portion of this is kind of in the red. So this one would be even whiter, okay? And it'll still be blue, but there's going to be less blue compared to this one, right? This one here, strongest in the blues and a little less in the warmer colors, right? So it's probably going to be a white star with just a hint of blue. I look at the 5,000 degrees Kelvin, right? This starts peaking in the yellow and green, and we're probably seeing like equal amounts of the blues and the warms. The blues dip off a little quicker, so we're probably going to see this as being like a yellow white star. Okay, down here, an object or a star that's 4,000 degrees Kelvin, right? We see our cooler colors, there's very little, and we see a lot of warm colors. So this star is probably going to be an orange-reddy star. So temperature affects the way radiation is given off. The hotter the object is, the more it pushes towards blue, and the cooler the object is, the more it pushes towards being red. So When we look up at the night sky and we see red stars and blue stars, particularly if we look at like Orion, right, and you can see different colored stars. Right? Betelgeuse is in the top left-hand shoulder of Orion, I think. Right, and Betelgeuse is an old red giant. I think it's a red supergiant, if I remember correctly. But anyways, it's a lot cooler, right, than the bluer stars and the rest of Orion. So here we see three different black body curves as well. Okay. This star here, 3,000 degrees Kelvin. Right? The peak is in infrared, so we can't see infrared. But the highest part in the visible spectrum we see is in red. We see more red than the blues, so this would be a red looking star. This star here, right, we're kind of peaking here at the blues, right? But all the colors are represented quite well, so it's going to have white in it. Right? But if we look, only at like maybe a third of the curve is in the cool colors, and 2/3 are in the warmer colors. So we're probably going to shift a little bit more towards the warmer colors, right? And have a whitey yellow tinge. This star here, the peak is in ultraviolet, which we can't see. And we're going to see all the colors, red, red, orange, yellow, green, blue, indigo. We're going to see violet. We're going to see all the colors, but it's going to be white, but we're peaking at the in the bluey violet area, so it's going to be a blue white star. And these two radiation laws that relate to black body curves, I'm not too worried about you knowing these, so don't try and memorize these. Right? So, Wien's law. This states that the hotter the object, the shorter the wavelength, or the more blue the light will be, which we already talked about. Stefan's law says that the total energy emitted is proportional to the temperature of the object to the fourth power. Right? So if we, for example, here, doubling the temperature of the star increases the radiation emitted by the power of 16. Okay, tripling the temperature, tripling it to the power 4, increases the radiation by a factor of 81. Okay, so the hotter you get, the more brilliant or intense the radiation becomes by a factor of 4. Okay, so we've talked about how light can tell us about the contents or the um, the element contents of a star, and now we've learned that how light relates to temperature of the star. So looking at stars, we can now gain a fair bit of information. We know what elements are in their atmospheres, right? And we know roughly how hot they are based on their temperatures, based on black body curves. Okay, so I'm going to stop it here. I'll upload this. It's going to take a while to buffer, then I'll upload it. And you're going to be doing your galaxy test and finishing that off. Then on Tuesday, we'll start talking about stellar evolution. Right? Okay. I hope you have a wonderful weekend.